In this video, I'm going to teach you the basic derivative rules. Oh look, it's baby's first derivatives! Aww! If you appreciate the content, please give it a like. Before we go any further, let's review what derivative means. Here's the graph of f of x equals x squared. Earlier in the unit, we learned that the derivative of a function is the slope of the curve at a point. So the derivative f prime at c means the slope of f at x equals c. The key word here is slope. For example, f prime at 1, the derivative of f at x equals 1, means the slope of the tangent line at x equals 1. In this case, that slope is 2. But how do we generalize that? How do we come up with an expression for the derivative of f at any x? In other words, how do we come up with a formula that gives the slope of the curve at any point? There are two different notations for derivative that we use in AP Calculus. Given a function y equals f of x, the Leibniz notation for derivative is dy dx, or d dx of f of x. The Lagrange notation for derivative is y prime, or f prime of x. When you want to evaluate a derivative at a specific value of x, like x equals 3, for the Leibniz notation, you write dy dx, you put a vertical line, and at the bottom, you put x equals 3. For the Lagrange notation, you simply write f prime at 3. Let's practice using the notation. The line tangent to the graph of f of x equals x squared at the point 5, 25 has a slope of 10. This is a long way of saying the slope of f at 5 is 10. In the Lagrange notation, all of this information can be captured with the expression f prime at 5 is equal to 10. It's a little more complicated for the Leibniz notation. We would have to say d dx of x squared at x equals 5 is equal to 10. How about the derivative of f of x equals x squared is 2x? Using the Lagrange notation, you can write f prime of x equals 2x, or in the Leibniz notation, it's d dx of x squared equals 2x. How do we express that the second derivative of f of x equals x squared is 2? The second derivative means the derivative of the derivative. It's the rate of change of the rate of change. For the Lagrange notation, the second derivative is expressed as f double prime. For the Leibniz notation, there's no way to directly read these symbols. We simply write this and say the second derivative of x squared is equal to 2. Assuming that y equals f of x, you will often see the Leibniz notation for the second derivative expressed this way. Notice that the superscript of 2 comes before the y. So here's your first derivative rule. Given a function in the form x to the n power, where n is a constant, the derivative of this function can be found by taking the exponent and putting it in the front, and then you write x, and the exponent is now reduced by 1. So n will become n minus 1. For example, given y equals x to the 7th power, y prime, the derivative, will be 7x to the 6th power. I'm going to use this simple derivative rule to try to make a few connections. The derivative of the function x will always be 1. This comes up so often that I do want you to simply memorize this rule directly. The derivative of x with respect to x is 1. However, here's the first connection I want to make with you. The function x can be thought of as y equals x to the 1 power. In that form, we can use the power rule that I just taught you. You bring the exponent out to the front, so this would be 1x, but then you reduce the exponent by 1, making this 0. Hopefully you learned in a previous class that when you raise something to the 0 power, it becomes a 1. So this part goes to 1, leaving us 1 times 1, which is 1. Here's the second connection I want to make. The derivative of a function means the slope of the curve at any point. X is the curve y equals x. So what is the slope of that curve? Picture the graph of y equals x, which is a diagonal line at like a 45-degree angle. We know that the slope, y prime, is 1. Here's the last connection I want to make. We've learned that for the Leibniz notation for the derivative of y with respect to x, you can either write d dx of y, or you can write dy dx. Similarly, the derivative of x with respect to x can either be written like this, or you could write dx dx. Obviously, dx over dx is going to equal 1. Can you guess the rule for the derivative of any constant c? Well, any function y equals c is going to be a horizontal line at c. And derivative means the slope of the curve. And we know that any horizontal line is going to have a slope of 0. So the derivative of any constant is 0. For example, given the function y equals 4, y prime equals 0. Let's see if we can come up with an expression for the derivative of the sine function by graphing the derivative at key points. Remember, the derivative is the slope of the curve at a point. So we need to find the slope of this graph at key points. Let's start right here. What do you think is the slope of the tangent line at 0? Well, the tangent line right here is looking like this. Alright, hopefully you can see that the slope seems to be 1. It's just about at a 45-degree angle, or in radians, this appears to be pi over 4. The slope of the curve at 0 is 1, so we're going to put a point right here at 0, 1 because we are graphing the derivative. What's the slope of the curve at pi over 2? At pi over 2, we clearly have a horizontal tangent line. Therefore, the slope is 0. Since the slope is 0 at pi over 2, let's put a point at pi over 2, 0. What do you think the slope is at pi? The tangent line appears to have a slope of -1. So let's put a dot at pi, -1. What do you think the slope is here at 3 pi over 2? It looks like another horizontal tangent line, so the slope is 0. So we'll have a point at 3 pi over 2, 0. Let's do one more. What's the slope at 2 pi? Just like at 0, the tangent line at 2 pi appears to have a slope of 1. That gives us a point at 2 pi, 1. Can you guess the derivative rule based on the slope pattern? How about now? Hopefully you can recognize this as the graph of the cosine function. So memorize this rule. The derivative of sine x is cosine x. Kind of wild, right? I find this interesting. It turns out that the cosine function gives you the slope of the sine function at any point. Let's use the same strategy to find an expression for the derivative of the cosine function. Will it turn out to be the sine function? We'll see. What's the slope at an x value of 0? We have a horizontal tangent line at 0, so the slope is 0. What's the slope at pi over 2? At pi over 2, the tangent line seems to have a slope of -1. What's the slope at pi? We have another horizontal tangent line at pi, so the slope here is 0. What is the slope at 3 pi over 2? At 3 pi over 2, the tangent line has a slope of +1. And finally, what's the slope at 2 pi? Just like at 0, we have another horizontal tangent line at 2 pi, so the slope is 0. Does that mean that we were right with the guess that the derivative of cosine is sine? Not quite. Hopefully you remember that this is upside down compared to the parent function y equals sine x. So this is actually the graph of negative sine x. So that's the rule I want you to memorize. The derivative of cosine is the opposite of sine x. If you take the derivative of a function that has a constant out in the front, you are allowed to just bring the constant down unchanged and then multiply that by the derivative of the remaining function. Again, if you are taking the derivative of a function that has a constant in the front, you simply bring down the constant unchanged and then go on to take the derivative of the remaining portion of the function. We just learned that the derivative of sine x is cosine x. So the derivative of 4 sine x is simply 4 cosine x. This is the combination of two basic derivative rules that you already know. This comes up all the time. I just taught you that if you want to take the derivative of any function with a constant in the front, you're allowed to move that constant to the front of the derivative. But earlier I taught you that the derivative of x is 1. So we have c times 1, which is just c. So go ahead and memorize that the derivative of cx is c. For example, if y equals 5x, then y prime is 5. Earlier we had the power rule, which was the derivative of x to the n power. The general power rule will be the derivative with an extra constant a in the front. According to the power rule I taught you before, you can move the n to the front and reduce that exponent by 1, so n to the minus 1 power. I already taught you that when there's a constant in the front, you can just bring that constant down unchanged and then go on and take the derivative of whatever comes next. So that's the power rule. It's actually more simple than I just made it look. If I want to take the derivative of 5x to the 7th power, I can bring the 5 down unchanged, I can move the 7 to the front, and then reduce that exponent by 1 so it becomes x to the 6th power. Obviously, 5 times 7 is 35. So in practice, we don't show that extra step. To take the derivative of 5x to the 7th power, we move the 7 to the front and multiply by the 5, and we just write 35. Then we reduce the exponent by 1, and we have 35x to the 6th. It's often easier to find the derivative if you rewrite the original function first. For example, y equals the square root of x is the same as y equals x to the 1/2 power. Now we can use the power rule, which tells us that to take the derivative, we move the exponent to the front. So we will have 1/2 x to the something, and then the new exponent will be 1 less than the original exponent. 1/2 minus 1, if you need to, think 1/2 minus 2 over 2, is going to be negative 1/2. So we will have 1/2 x to the negative 1/2 power. To take the derivative of y equals 5 over x, let's rewrite this as y equals 5 times x to the negative 1 power. Now we can use that power rule. We can move the negative 1 to the front and multiply by this 5, so that gives us negative 5. Then we reduce the exponent by 1, so negative 5x to the negative 2 power. For x over 5, we are not going to write 5 to the negative 1 power. We are going to recognize that x is like 1x. And notice that here we have basically a constant of 1 over 5 in the front. So x over 5 is equivalent to 1/5 x. And the derivative of a constant times x is just the constant. Again, because you can just bring the constant down, and then the derivative of x is 1. Let's practice taking the derivative of some functions that have more than one term. For number 1, We do not yet know how to take the derivative of something times something, so we need to rewrite this using the distributive property. This is the easier way anyway. We have not yet taken the derivative. We've just rewritten the original expression. But now we can easily find the derivative term by term. We use the power rule on this first term, moving that 2 to the front and reducing the exponent by 1, which we don't need to write. And then the derivative of 2x is just 2. Whenever you take the derivative of a constant times x, it's just the constant. We do not need to rewrite number 2. We can just take the derivative term by term. So y prime equals. Using the general power rule, we move the 3 to the front, multiply by the 1/5, so that's 3/5. Then we reduce this exponent by 1, so that's 3/5 x squared. Time for the next term. When there's a constant in the front, you can just bring down that constant, and then take the derivative of whatever comes next. We have memorized that the derivative of sine x is cosine x. We have also memorized that the derivative of a constant is 0, so the 7 goes away, and this is the final answer. Pause the video and try these 3 examples on your own. For this first one, it might be easier to rewrite the original function as 5/4 x squared. Notice that we have not taken the derivative yet, so the d dx is still here. Now we use the general power rule. Taking the 2 and multiplying by 5/4 gives us 10/4, which simplifies down to 5/2. Then we reduce the exponent by 1, so that'll be 5/2 x. And that's the final answer. Now that we have taken the derivative, you do not write the little d dx anymore. If you do, it's incorrect. Like if I wrote d dx, oh, you know what? This is a common mistake. That's what I wanted to emphasize. Do not write this. No. Don't put d dx equals. Writing d dx equals something would be just as silly as taking the square root of 9 and then writing the answer as square root equals 3. We do not do this. Just like we write the square root of 9 is 3 with nothing in front, the derivative of 5/4 x squared is just 5/2 x with nothing in the front. For the second one, you want to rewrite the original function as x to the negative 1 power. We have not taken the derivative yet, so the d dx is still there. Now we use the power rule. You move the negative 1 to the front, so that's negative like that, and then you reduce the exponent by 1. So negative x to the negative 2 power. Now we have taken the derivative, so you do not write d dx, and you definitely do not write d dx equals. For the last one, think of 6 times the square root of x as 6 times x to the 1/2 power. One more time, we have not taken the derivative yet, so the d dx should still be there. Now we use the power rule and multiply the 1/2 times the 6, and we get 3. Then we reduce the exponent by 1. 1/2 minus 1 is negative 1/2. And that's it. By the way, these are all acceptable answers for a free response question. However, half of the AP exam is multiple choice, so I need you to get comfortable with recognizing answers in different forms. Obviously, 10/4x is the same as 5/2 x. X to the negative 2 power can be written as 1/x squared. Similarly, 3x to the negative 1/2 power can be written either as 3/x to the positive 1/2 power, or you could write 3 over the square root of x. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.